Welcome everyone. In this video I will present the first part of my plenary lecture delivered at the 9th Particles Conference last October. The lecture is entitled Recent Developments of Smoothed Particle Hydrodynamics Models for Simulating Violent Free Surface Flows. The YouTube version of the presentation is longer than the one delivered in Barcelona and consists of about 100 slides. Therefore, it has been divided into two videos. This slide shows the outline of the presentation. I will start with a brief introduction of my institute and to my research group. Then I will discuss the connection between Hamiltonian many-particle systems and the hydrodynamical equations in order to place the SPH method in a more general theoretical framework. We will see how the SPH equation can be derived within the context of a Lagrangian thermomechanical system. The last part of the presentation focuses on the main developments of the SPH method over the past decade. One key issue concerned conservation properties. I will show that scheme enforcing strong conservation laws may lead to numerical instability, which can severely limit the practical application of the model. Finally, I will introduce what I call modern SPH models. These models, developed in the recent years, are now capable to addressing emerging and highly challenging flow problems, as I will demonstrate in the final part of the presentation. I work at the Institute of Marine Engineering, which is one of about 100 institutes of the Italian National Research Council, or CNR. These institutes are organized into 7 departments, and the INM belongs to the Department of Engineering, ICT, Energy and Transportation. My institute is located in the southern area of the city of Rome. Here you can see some aerial photograph showing the two main elongate buildings of the institute. And these buildings host the towing tanks, which are among the longest in Europe. And on the left-hand side of this picture, it is also possible to see the circulating water channel. Thanks to these large experimental facilities, it is possible to perform tests on different types of model vehicles. Here, for example, you can see a ditching test of an aircraft model, as well as some seakeeping tests performed on two-ship model. In addition to the experimental activities, the Institute also carries out extensive research in computational fluid dynamics, with a focus mainly on marine and ocean engineering applications. My research group in particular is interested in the use and development of particle methods suitable for this type of application. In the second row of this slide, I have highlighted the youngest members of the group. Hongguan and Joelle are postdoctoral researchers, and Chiara is a permanent researcher. Our research activity started about 28 years ago. The main focus was the development of particle methods capable of dealing with flows involving gas-liquid interfaces which undergo large deformation and may even fragment. In addition to code development, we have also devoted a significant part of our work to the theoretical aspect of these methods. As a result, we have been able to collect useful and practical knowledge for the accurate simulation of a wide range of engineering problems. The smooth particle hydrodynamic method has been the main approach studied in our research activity. This method is characterized by 3 main feature. First, the meshless character. No computational grid is required, and the fluid motion is modeled through the interaction between arbitrarily distributed points. Second, the Lagrangian character. The flow is described by following the motion of the computational points, which are treated as particles. Third, the Hamiltonian character. The particle system can be formulated as an Hamiltonian system, which naturally preserves conservation properties such as mass, momentum, and energy. We will discuss this characteristic more in detail during the the course of this presentation. This slide shows one of the main benchmark problems we treated, that is a breaking wave. In the left panel you can observe a large deformation of the air-water interface with the formation of a plunging jet. In the central panel, this jet impacts the water surface below, generating a splash-up jet characterized by intense fragmentation and formation of multiple water droplets. Finally, in the right panel, after some time, it is possible to appreciate how the breaking process leads to a turbulent flow with several vortex structure and air bubbles entrapped within the liquid. If a numerical solver is able to correctly simulate this benchmark, it can then be applied to engineering problems, such as the simulation of wave patterns generated by fast boats or ship, or problem related to water impacts in naval, aeronautical, and aerospace industry, or problem of violent free surface flow related to coastal engineering, hydraulic engineering, renewable energy, or offshore industry. Or problem involving sloshing flows. Here, for example, you can see cases of violent flows occurring inside an aircraft wings, or inside a fuselage, or inside ships used for the transportation of liquefied natural gas. These types of flows are particularly interesting for us, since we have worked on several research projects in which we demonstrate that for sloshing problem, the SPH method is highly competitive when compared with more classical approaches such as the finite volume. This graph shows the number of publications related to the SPH method together with the corresponding number of citations. As you can see, the method is still in a phase of development. I was particularly lucky in starting to work on SPH back in 1998, when the method was not yet very well known and was often perceived as a rather unusual approach within the fluid dynamic community. Recently, I spent some time working with my colleague David Touzé on a review article on the SPH method, published in Reports on Progress in Physics. For those who may be interested, this paper provides more detailed information on many of the topics discussed in this presentation. We can now start discussing the SPH model within the framework of a Lagrangian thermomechanical system. Indeed, it is possible to derive the SPH equation starting from a more general framework, in which a fluid is modeled as a macroscopic system of discrete particles. Like some other particle-based models, the SPH equations can be derived by following two different conceptual paths, as described, for example, by the Italian professor Enzo Tonti. The first path is the most classical one in fluid dynamics. Starting from the physical problem, we write the governing equation as a system of partial differential equations, typically the Navier-Stokes equation, and then discretize them using integral interpolation techniques. Alternatively, we can directly write the equation of a particle system and then show that in the limit as the number of particles tends to infinity, the Navier-Stokes equation are recovered. To follow this second path, we start by defining a Lagrangian function for our particle system, which includes the kinetic, the potential, and the internal energies of each particle. The particle masses are assigned in the initial condition and remain constant throughout the time evolution. This assumption ensures mass conservation for the entire system. From the Lagrangian equation, the particle acceleration can be expressed as the result of conservative force field F together with the pressure forces, which appear as the third term associated with the particle interactions. These forces arise because particle motion modify the density distribution, which in turn affects the internal energy of the system. On the right-hand side of the equation, all non-conservative forces are included. This can be divided in two components. The first is the viscous contribution, related to the friction forces between particles. The second consists of non-conservative forces associated with kinematic constraints, for example, the fact that particles cannot penetrate solid boundaries. In addition to the Lagrangian equation, we can also write an energy equation for the particles. By taking its time derivative, we can naturally embed the first law of thermodynamics, which relates the time variation of the internal energy to the distribution of pressure and temperature and the time variation of entropy. By multiplying the momentum equation by the particle velocity and assuming that the particle system is isolated, we can simplify the energy equation in this form. In this formulation, the entropy production is associated with the viscous forces, and we can also account for heat fluxes exchange Q between the particles. In order to comply with the second law of thermodynamics, the entropy production must be non-negative. How can we model the viscous force experienced by the particles? We can start by defining a Rayleigh dissipation function, phi. Here, Uij denotes the relative velocity difference between two generic particles, I and j. The friction forces are modulated through the action of a tensor A, which explicitly depends on the relative particle distance Rij. Since we need to satisfy these three physical constraints, the rigid body invariance, the conservation of the angular momentum, and the second law of thermodynamics, the tensor A can be reduced accordingly. This leads to a simple formulation in which the tensor A is expressed in terms of a scalar function g multiplied by the square of the projection of the relative velocity Uij onto the unit vector Eij, which is collinear with the vector Rij. As reported in the article cited on this slide, the dissipation function phi depends on the geometric dimension n of the problem under consideration, and this dependency can be made explicit in this formulation. I would like to emphasize that the viscous function g must be non-negative in order to comply with the second law of the thermodynamics. These are the equations of a general Lagrangian thermomechanical system represented in terms of particles, in which both the first and the second laws of thermodynamics are embedded. In order to close the system, an equation of state is required, linking pressure to density and entropy. It is worth noting that this framework is more general than the SPH model itself. To solve this equation, we need to specify three key ingredients. First, how particle density evolves as the particles move. Second, a consistent derivation of the viscous function g. Third, a consistent derivation of the heat fluxes Q. Therefore, in principle, different numerical models can be obtained by adopting different formulations for these quantities. Let's look at the choices that lead to the SPH models. As Professor Daniel Price emphasized during a keynote on SPH model, the central element of the SPH method is the evaluation of the density through a kernel-weighted sum. The rest of the equations follow naturally from Lagrangian thermodynamics. In other words, the key idea is that a continuous density field is obtained by using a kernel function W, which smooths the discrete particle masses across the physical space. It is important to note that different kernel formulas, such as the one shown here in blue, can be used leading to different SPH models. The choice depends on the specific fluid dynamic context in which the method is applied. For the particular choice adopted here for the density evaluation, it is easy to see that the kernel function directly provides an estimation of the volume occupied by the particles. Moreover, since the kernel function is radially symmetric, its spatial gradient has a simple structure. It is proportional to the vector Rij multiplied by a scalar function f, which, like the kernel itself, it is a positive function. In the next slide, I will show the relevance of this function f. Indeed, the kernel function f can be used to define a suitable viscous function g. In this formulation, an harmonic mean of the particle viscosity is adopted. As you can see, since f is strictly positive, it immediately follows that the second law of thermodynamics is satisfied. For the sake of simplicity, a constant viscosity field is assumed, and under this assumption the final expression reduced to the formula shown here for the viscous forces. Moreover, the kernel function f can also be used to define the heat fluxes Q between particles, again adopting an harmonic mean for the thermal conductivity. Assuming that the kernel conductivity is constant in space, the final expression for the evolution of the particle entropy takes the form shown here. In this slide, we finally obtain the SPH equations. On the left-hand side, we have the continuity equation together with the particle volume and the density evaluation. The momentum equation is shown in the center, while on the right-hand side we report the entropy evolution equation. Particles are advected Lagrangially, and an equation of state link entropy, density and pressure. In some cases, it is preferable to use the internal energy formulation instead of the entropy one. By again invoking the first law of thermodynamics, we can reformulate this equation accordingly. As you can see, this change of variable requires the knowledge of the time variation of the particle volumes. This can be obtained simply by taking the time derivative of the particle volume expression, where the function f appears once again. This slide presents the first SPH scheme. On the right-hand side, its conservation properties are summarized. Mass, momentum and energy are conserved, while entropy production is always strictly positive. In this other slide show the second SPH scheme, which is in fact the original formulation developed in the astrophysical context. This scheme is slightly different from the first one, since it was derived for highly compressible flows. For this reason, the density evaluation is formulated in a different way. As you see, the mass is inside the kernel, inside the summation. On the other hand, unlike the scheme 1, this formulation cannot be applied to multiphase flow characterized by large density ratio. The conservation properties are the same. The first two articles on the SPH method are those by Lucy and by Gingold and Monaghan, both published in December 1977. Each of these papers has received about 10,000 citations and can therefore be considered a milestone for the development of the method. Lucy was the first to introduce the idea of estimating density using a kernel function, while Gingold and Monaghan gave the method its name. These two papers are often cited as original reference for SPH. However, a careful reading shows that neither of them contain the SPH scheme discussed early in this presentation. In particular, the equations proposed in these early works are not conservative with respect to momentum and energy. Indeed, it was in another paper published 5 years later, and again by Gingold and Monaghan, that the derivation of SPH equation from a Lagrangian formulation was established. In this work, the conservative SPH scheme was obtained and subsequently adopted by most of the research community. It is quite remarkable that the number of citations of this paper is much smaller compared to the earlier ones. Another milestone article for SPH is this one, simulating free surface flow with SPH, published in 1994. In this work, Professor Monaghan had the key intuition that a method originally developed in an astrophysical context could also be applied to free surface flows. This represents a fundamental step, as it opened the way for a wide range of engineering applications of the SPH method. Indeed, the original SPH formulation cannot be applied directly to the free surface flow. The density and the particle volume expression presented earlier fail in the vicinity of a free surface due to the truncation of the kernel support. How did Professor Monaghan overcome this problem? The solution consists in deriving the particle volume, or equivalently the particle density, with respect to time, and then integrated numerically the resulting continuity equation. In fact, the time variation of these quantities is not affected by the truncation of the kernel support at the free surface. Here we have the third SPH scheme, which can be applied both to free surface flow and multiphase flows. As you can see, the continuity equation is written in terms of the time derivative of the density. As shown in the sketch on the right, the fluid domain may include different liquids or gaseous phase, solid boundaries, and a free surface separating the liquids from an empty region E. The conservation properties are preserved in the scheme as well, but one question arises. When considering an envisaged fluid, the SPH model is still an Hamiltonian particle system? The answer is that this SPH scheme is a non-canonical Hamiltonian system. Indeed, in the scheme number 3, the density becomes an independent dynamic variable since it is no longer a function of the particle position alone. The time integration of the continuity equation introduces an approximation which breaks the underlying Hamiltonian structure of the particle system. As a consequence, the time reversibility is lost. However, this does not affect the conservation of mass, momentum and energy. This introduces the first compromise. During this presentation, I will show that the history of SPH is essentially based on a series of compromises introduced in order to properly handle flows of increasing complexity. Coming back to the SPH scheme number 3, if we consider the limit in which the number of particles tends to infinity, it is possible to recognize within the SPH formulation the differential operators of the Navier-Stokes equations. Indeed, it can be demonstrated that the SPH equations are consistent with the Navier-Stokes equations. It is also possible to proceed in the opposite direction, starting from the Navier-Stokes equation, discretizing them on a finite number of particles, and then deriving the SPH equations. There is not enough time in this presentation to explore this second approach in detail. What I would like to emphasize is that this procedure leads to a fourth SPH scheme, which differs from the third one only in the definition of particle volumes. For example, you can see that in the fourth scheme, the particle volume with index J appear in place where in the third scheme, volume with particle with the index I are used. So, if the particle volume distribution is characterized by a low spatial gradients, the two schemes are practically equivalent. In this slide, we summarize the main advantage of the SPH scheme number 3 and number 4. the conservative properties are preserved and the second law of thermodynamics is respected. Since particles are transported in a Lagrangian manner, the free surface kinematic boundary condition is automatically enforced. Concerning the free surface dynamic boundary condition, this is also implicitly satisfied, as demonstrated in the reference reported in this slide. These two last points are particularly important since they imply that there is no need to explicitly detect free surface particles or to impose the boundary condition numerically. I would like to stress that the success of the SPH method over the last decades is largely due to these properties. On the right, in red, the first compromise we have to accept is highlighted. Before closing the first part of this presentation, I just want to recall 3 milestone articles about the mathematical proof of the SPH convergence, which is a quite complex topic. The first article on the SPH convergence was done by some Italian colleagues in 1998. This is a typical Italian story where we were the first in doing something new, but we were not able to use this advantage with respect to other countries. The other 2 relevant articles are from French colleagues, again linked with the topic of the convergence of the SPH and also in a more general context of particle methods. This concludes the first part of this presentation. In the second video, we will move from the theoretical foundation to the numerical aspects of SPH, focusing on instability, conservation issues, and on the modern formulation that make the method suitable for challenging engineering applications. If you found this presentation interesting, I invite you to continue with the part 2, where I will discuss recent development and real-world application of SPH for violent free surface flow. Thank you very much for watching.